I am Aurèle MAHEO from Télécom SudParis. I'm going to present our contribution, which is the Serverless Shell. First, let's remind what is serverless computing. Serverless computing is a cloud service. It's a recent paradigm, and it allows to execute functions on a remote platform, specifically fast platform, function as a service. The function execution is enabled by complete runtimes. So practically, from a user standpoint, the user defines his functions. It deploys the function on the remote platform and executes the function each time for each function call. And the user pays only for the resource, compute resource he uses, and for the execution duration. So serverless computing comes with several benefits. Unlike other cloud solutions, the user doesn't need to worry about the server provisioning, the machine administrations. He only needs to focus on his function. Serverless computing exposes a massive parallelism, so it's very easy to instantiate thousands of functions. So it's a very highly scalable solution. But for the counterparts, as there are many serverless computing vendors like AWS or Google with AWS Lambda, Google Cloud Function, Microsoft Azure Functions, there is not yet any unification of the API. So the vendor propose different APIs. Also, since each function is instantiated and isolated from another, that means that the state after the code at the end of the function execution is lost across the functions. That means with serverless functions are stateless. So we can imagine different applications for the serverless computing. For example, data processing. And several languages are available for data processing, like example R, Python, or UNIX Shell. UNIX Shell is very interesting because it's a mature language used for data processing or system administration, and it's very easy to fetch data, process data, manipulate the data, research for patterns, and with a one-liner. For example, we can display a data set, use pipe operator to combine with a command A, a command B, etc. It's also possible to express parallelism with using a GNU parallel, in addition to a UNIX shell. But UNIX shell plus GNU parallel come with its limitation. Limitation made by the limits of the physical machine, on the configuration of the physical machine. So this is a problem when you want to process large data sets, because the user will encounter bottlenecks. That's why it may be interesting to combine a UNIX shell with the serverless approach in order to reuse existing code base and benefits from the parallelism offered by the serverless computing. So we present here our solution, which is the serverless computing, which consists of combining the benefits of the serverless computing with a UNIX shell language, and its simple syntax. So the idea is to adapt the UNIX shell for serverless computing. In that, with the serverless shell, we prefix the UNIX script with the shell keyword, which is the software. Consequently, we are able to execute our UNIX script not on the local machine, but on the remote platform. We intend to be compatible with the standard shell scripting in order to have access to large legacy code. We present a modular design. So the design includes a serverless platform, an executor service in charge of transmitting the shell command to the platform, and we have additional features to support stateful programming. Stateful means use of shell objects in order to leverage a parallelism. For that, we can plug serverless shell to a distributed data storage in order to have access to a distributed file system, and the serverless shell rely on an inter-process communication layer in order to execute shell objects and execute parallel semantics like a barrier. Here is a basic example. So if a user wants to display the root directory on its local machine, he will type ls-C/ and this command will display the root directory on the local machine. If we prefix this command by shell, we will display the root directory on the function instance. Now let's have a look to the system design with a very simple example. Let's consider the end user working on his laptop he just wants to display the number of lines of a given file named foo. So if he wants to execute this command on the remote platform, he will prefix by shell. So on the first step, the user contacts the fast platform and transmits his shell command. The second step, the fast platform instantiates an shell function. Step 3 and step 4, shell will fetch the file foo on the distributed file system. And step 5, the standard output is returned to the user. Let's have a second example. So the user wants to execute a parallel command using GNU parallel, and he wants to execute a barrier named foo. So he will transmit the parallel shell commands to the fast platform. Secondly, the fast platform will instantiate 3 shell functions. And on the third step, each shell instance will synchronize on the barrier foo using the IPC layer. Now let's see a demo which calculates, showing a shell calculating, performing an average calculation. Now we are on an EC2 instance. The server shell is built, and we want to deploy the server shell to the fast platform using a configuration file. To use the IPC layer, we'll need to start the IPC layer on a remote server. So we need to fill the IP address, the last line of the configuration file. Now we deploy the serverless shell function. Now we execute a simple command. We display the content of the function instance. Now we have a look to the example containing a average calculation with two versions. First, we want to mine a large dataset, command call dataset. We have input. We have an index file containing with each line containing a line tarball. We want to parse the 1,000 first lines. Now we have two versions, and we parse the index file on each line. The S shell will fetch a dataset. Then we'll look when it will search for a specific content. Now we store the value associated to the content, and we perform a final average using awk, so stateless version. With the stateful version, we use parallel semantics like a counter to perform to calculate the final average. Now we launch the stateless version. Now we launch the stateful version. Okay. Now, let's see the technical part. The serverless shell was developed in Java language, and the software contains around 3,000 lines of codes. And serverless shell was built as a native binary using a GraalVM Java implementation. For the distributed file storage, we use AWS Elastic File System. The inter-process communication layer was implemented using the distributed shared object software component, which is part of the Crucial project. For the evaluation, the serverless platform, we use AWS Lambda as a serverless platform. And S-Shell was run on an EC2 instance containing 8 compute cores. For the evaluation, we intended to identify the bottleneck and enable a performance breakdown and isolate different components like the latency to invoke S-Shell, the compute parts, and the time to force transfer between the Elastic File System and the AWS S3 repository. We wanted to compare the serverless shell with 2 micro benchmark and a large-scale application, cluster-based application. Now, it's important one important thing is as we want to run a shell using GNU parallel, if you want 100 jobs, we will run 100 instances of serverless shell. That means if we build the server shell with a traditional Java implementation, non-native, that means we start 100 Java virtual machines, which leads to obviously to a bottleneck, and in terms of memory footprint and the execution time. So this plot shows the performance, the execute time, and compare the execute time between the non-native Java implementation and a native implementation using GraalVM. So we see that when we build the serverless shell using GraalVM, which means as a native binary, we obtain a speed up of around 68 with 80 parallel jobs, which is very, very important. On this slide, we focus on the invocation latency. So when we talk about invocation latency, we isolate the latency coming with NUC parallel and the latency coming with shell. We see that we have different runs, and we are spanning from 20 to 80 parallel jobs. And we see that the latency coming with shell decrease as we increase the number of jobs, but we can observe that the GNU parallel doesn't scale well as we add the number of jobs. So we can observe a stagnation when we increase the number of jobs if we consider the overall time completion. Then we consider first a micro benchmark, which consists in starting from a repository, image repository on the distributed file storage. We want to copy each image to each function instance, generate a sample, and copy back the sample to the local directory. So we consider three components: the compute part, the download part, and the invoke latency. So we can see that we are able to lower the completion time as we increase the number of parallel jobs, but the invoke latency increase. If we consider a second micro benchmark, which consists of parsing a 40 GB of a scan of the full internet port scan of the port 80, the micro benchmark consists of isolating the IP address and the autonomous system, merge these two components, and count the number of IP address and autonomous system. So we perform the evaluation considering two factors: one, the price, and two, the speed up, with basically three versions of the micro benchmark. First is a first sequential version. Secondly, an execution on a native machines on a EC2 AWS EC2 instance with the number of compute cores spanning from 16 to 98. The third version is shell. We can observe that shell provides the best results, the best trade-off in terms of price and speed up. The explanation is, unlike a classic cloud solution like EC2, where we reserve a machine, we allocate a machine, and we use a machine to perform parallel jobs, and it's not obvious that all the resources, all the compute cores are properly used. We can be sure that with a serverless approach, we use only the resource required to perform the computation, which is very interesting, and we wish to optimize the cost, the price. Then we consider a large application which consists in mining a common crawl dataset, parsing the page of the web domain pages, and filtering the outgoing links, and then as a result, we are able to perform a ranking of the web domains. So we consider 5 components. First, the invoke latency, the download part, the compute part, which means the data processing itself, the synchronize part, because we need to synchronize the results between all the function instances. And at last, we consider the sort part. We consider the sorting. So we can see that as we increase the number of parallel jobs, we are able to minimize the execution time, even if the invoke latency increases. So we compared the serverless version for this given problem. We compare our serverless version, serverless shell, with link run, which is a cluster-based solution. The link run involves a pipeline and involves AWS S3, Elastic MapReduce, Apache Spark, and a database, Postgres. In the array on the below of the slide, we can see that we are able to complete the execution in less than half an hour, with a number of lines of codes much lower than the link run solution, with a much lower pricing, and with a similar dataset size. As a conclusion, we presented the serverless shell, which consists of adapting the UNIX shell for the serverless. With S shell, with a simple semantic, we are able to reuse a code base by only prefixing the UNIX script with the S shell. Our solution proved to be efficient to mine large datasets, and we were able to support stateful computation, which means perform parallel computation using parallel semantics like barrier, counters, or map, etc. Thanks to the distributed file system on an inter-process communication layer. For future work, we want to support auto-parallelization. For this, we intend to use. We are using the existing work, which is named PASH, which consists of parallelizing UNIX input script shell, and produce parallel version of the script shell using NAND pipes. We intend to add a backend to this work to produce a version using the file system, and another version using socket communications. Also, we want to address other system mechanisms like direct socket connection or implement pipe operators in order to support stream processing. Thank you.